Hello again, this is Ray, and we're continuing to cover section 2.5. This is our second objective. So in this objective, we will be looking at the distance between a point and a line. Now, a couple things before we begin. We need to know the equation of a line. If we have an equation of a line, you should be able to extract a point on the line and the direction of the line. So we need those two pieces of information. We need to be able to extract x naught, y naught, z naught from the equation of the line, and then we also need to be able to extract the direction. So let's say this is p naught in the point, this is the direction vector d, a, b, c, or whatever. So that's one piece of information that you should know. Another piece of information that you know is that if you have two vectors, they span a parallelogram. And those two vectors that span a parallelogram, that parallelogram has an area. And it turns out that the area of that parallelogram is, if we call this u and v, the area of that parallelogram is going to be the magnitude of u cross v. So we should know those two pieces of information, and then using these two pieces of information, we should be able to find the distance between a line and a point. So the idea behind here is kind of sketched out in this bullet list. So find a vector connecting the point and the line, find the area of the parallelogram spanned by this point and the direction of the line, and then the area of the parallelogram is the base times the height, and then we're going to divide the base. So let's actually take that a little bit more slowly and figure out what's going on. So what's going on is that you have a point here. Let's call it again P naught. So essentially I'm going to redraw this graph or this sketch drawing over here. And then you have a direction here, and let's call that direction D for the base. And then you have some point that is not on this line. So let's call this point I don't know, let's call it, this is P naught. I think we can call this P without the subscript to say, okay, that's just another point that's not on the line. All right, so the first step is to find a vector connecting the point and the line. So we have, we can choose any point. Let's just choose the easiest point here in the line. And so that point here is going to be this vector that connects these two. So we would do some sort of subtraction to connect those 2 points. And then now it turns out that this actually forms a parallelogram that kind of looks like this, and we can find the area of that parallelogram. So whatever the area of that parallelogram is going to be, let's do this in green. So area is going to be given by the magnitude of, let's call this vector v, just to give it a name, the magnitude of v cross the direction vector d. And then it also turns out that to find the area of a regular parallelogram, I don't know if we know this, but if you have some random parallelogram that doesn't depend on vectors, oops, that's not quite a parallelogram. This is a little bit better. To find the area of this parallelogram, you need to find a base and then the height. Well, this is not quite a perfect rectangle, but it's a little skewed. But the height of that parallelogram will give you the area. So this is, if this is the base and this is the height, then the area is equal to base times height. So if we look at our scenario here, the base looks like it's going to be this distance or the magnitude of your D. So your base is going to be the magnitude of D. And then the height, well, we don't know the height. This would be the height. So the area, we're saying, is also equal to the base, the magnitude of D, times the height. Well, it turns out that this distance here from the point to the line is, in fact, the height that we're looking for. So if we go ahead and solve for h here, then we're going to have h is equal to v cross d, magnitude of those cross product of those two vectors, divided by the magnitude of your direction vector. All right, so a little bit neater. Here's the setup. L is a line passing through the point P, and then M is going to be, so I think the way this is set up, this is M. So let me change my notation and call this M. So M is another point that's not on the line. Then we make this vector V to go from P to M, and then the distance from the point M to that line, which is going to be this vertical line H that we're looking for, is going to be given by this expression, which is what we found over here. All right, let's do an example. Here is our example, and let's just look at the formula. So according to this, we need our point P and M. So I think it's clear that this is M. This is going to be the point that's not on the line. So this is the equation of the line. It's written in parametric form. We need to extract our P, our point on the line, and our D, direction vector of the line. So I think I'm looking at this as putting this into X and Y form. This is going to be -1 minus t, comma, -t, comma, 2. That's closer to the vector form. And what I'll do is I'll take out the things that don't have a t. So I have a -1 constant, and there's nothing here, so I think the y component is going to be 0, and the z component is just 2. And then extract the stuff with a t in it. So this has a -1 times t. This also has a -1 times t. And the last one does not have a t, so the coefficient of that must be equal to 0. All right, so if I write it like this, I can see the point. I know I drew this as a vector, but a vector and point are essentially the same thing, so it doesn't matter how you look at it. So I think this is my P, and this is going to be my direction vector D. Okay, so now I have a point and a direction, and I have M. So I need to find V. So let's get V going. V is going to be the vector from P to M, and it's going to be head minus tail. Let me write this out just in case. The head is 4, 3, 5, and then the tail is the point -1, 0, 2, and so that will equal to 4 minus -1, so that's a 5, 3 plus 0, and 5 minus 2. So I believe this is what we're looking at as the vector V. We have the direction vector here, and so at this point we will want to take the cross product of V and D. V cross D is going to be equal to, we'll do our work for the cross product. The V vector is 5, 3, 3. The D vector is -1, -1, 0. And then in doing the cross product, my I direction is going to be 3 times 0 is 0, minus -3. That's going to be a +3. The second component will be a negative, and then that's a 5 times 0, so that's 0 minus negative 3. So minus negative 3 is a positive 3, but that j component has a built-in negative sign, so we'll keep that there. And then the k component is going to be negative 5 minus negative 3, so that's negative 5 plus 3, that's negative 2. So that is my vector v, or that's my cross product between v and d. Now to find the area of the parallelogram, we take the magnitude of that. So magnitude of v cross d will equal to the square root of 3 squared plus 3 squared. It's negative 3, but I'm going to square it so it'll be positive. And then the last one is negative 2 squared, or just 2 squared. So we have a couple of 9s and a 4. So 18 plus 4 is 22. And this is under a square root. Okay. Now we need one more thing. We need the magnitude of d. So let's go ahead and find the magnitude of d. And that's the square root of 1 plus 0. That's root 2. Okay. So then finally our distance, our solution distance between the point M and the line given here is going to be given by the magnitude of v cross d over the magnitude of d, and these are all vectors. So this is root 22 divided by root 2. I think that simplifies to square root of 11. All right. Okay, so things to remember. It's good to know the formula, but it's also good to know how the formula was derived. It's derived by this. This picture says a lot. And then once you have that formula, the next thing to do is be able to extract the point and the direction from the equation of the line, whatever form it might be in, and then construct your v vector, find the cross product, find the magnitudes, and then divide. All right, I hope that helps. Good luck.